Hey everyone, welcome to another explainer. Today we're taking a seriously high-energy journey under the hood of the electric vehicle. But right off the bat, I want to start us off with a quick history test. You might think EVs are this brand new, modern invention driven by 21st century tech. But get this, the very first electric vehicle actually predates the American Civil War. Yeah, all the way back in 1835. Okay, so here's our agenda for today's explainer. We're going to cover 1. The return of the EV. 2. The heart, which is battery chemistry. 3. The brain, or power electronics. 4. The muscle, meaning EV motors. 5. The magic of regenerative braking. And finally, 6. Electrifying the last mile. Let's get right into it. Starting off with Section 1, the return of the EV. So back in 1835, American inventor Thomas Davenport built the first EV. And it's actually fascinating because by the year 1900, electric city cars were literally everywhere. They made up 38% of all cars. They absolutely dominated the streets long before those gas-guzzling engines took over the global market in the 1920s. It really wasn't until the 1990s, sparked by California's Clean Air Act, that EV development saw a serious revival. Now, what's really wild is the cultural shift that caused EVs to lose that early lead. Part of the reason gas cars won out early on was simply because maintaining a dirty internal combustion engine, hand cranking it, fixing the gears, was considered a quote-unquote masculine challenge by male drivers. Because early electric cars were so smooth and maintenance-free, they were actually stigmatized as being just for women. So yeah, the internal combustion engine prevailed largely on social attitudes and, of course, cheap gas. Moving right along to Section 2, the heart, battery chemistry. When we compare modern battery chemistry side by side, we see a pretty sharp contrast between the two main titans, LFP and NMC. LFP, which stands for lithium iron phosphate, gives you massive longevity and safety. You can literally charge it to 100% every single day without ruining it. On the flip side, NMC, nickel, manganese, cobalt, packs a much higher energy density. That gives you maximum range and way better cold weather performance, though it does come at a higher cost. So which should you choose? Well, your lifestyle really dictates your battery here. If you live in a warm climate, you prioritize longevity, and you charge at home daily, LFP is your absolute champion. But if you take frequent long trips in the freezing cold and rely heavily on fast charging, you're definitely going to need the NMC to get you there safely. All right, let's look at Section 3, the brain, power electronics. The most vital organ in the brain of the car is the traction inverter. See, your battery stores power as direct current, or DC, but your motor? It needs alternating current, or AC. The traction inverter seamlessly translates that DC power into the AC power needed to drive the wheels, and it dictates your speed and torque with incredible precision. Then we have the onboard charger. This handles the exact opposite task. When you plug your car in at home, the grid gives you AC power. The onboard charger takes that AC power and converts it into DC power to safely fill up your battery pack. It's basically the ultimate gateway between your house and your car. Finally, we've got the DC-DC converter. Your main battery operates at a massive 400 or even 800 volts. That is enough to instantly fry your radio, your lights, or your windshield wipers. So the DC-DC converter steps down that massive voltage to a safe 12 or 48 volts to power all your delicate auxiliary systems, so everything just runs smoothly. So how are manufacturers putting these brains to work on the road? Well, the market has overwhelmingly settled on the two inverters configuration as the dominant setup. This beautifully balances all-wheel drive traction with efficiency. It allows for an independent motor on the front and rear axles without adding unnecessary weight and complexity. Next up, Section 4, the muscle, EV motors. The magic of the AC motor happens in this beautiful four-step sequence. First, the outer stationary part, the stator, receives three-phase AC power. This creates a chasing, rotating magnetic field, known as a magnetic flux. Then, the inner part, the rotor, interacts with that invisible magnetic field, which forces it to physically spin. Add a shaft, and suddenly, your wheels are moving. To achieve this spin, engineers constantly weigh two very different motor designs. First up is the induction motor. It's rugged, it's cost-effective, and it has low drag when turned off, but it's a bit less efficient at low speeds. Pit that against the permanent magnet motor. This one uses rare earth materials to deliver incredible torque and superior efficiency, but the catch is it creates permanent drag when you aren't using it. But hey, Smart engineering solves this problem by not choosing at all. Many companies, like Tesla, just use both in a dual motor synergy. They rely on the permanent magnet motor for that instant stop-and-go city torque. But when you hit the highway, the car turns off the induction motor entirely, letting it coast freely without any magnetic drag, which maximizes your highway range. Best of both worlds, right? Let's check out Section 5, the magic, regenerative braking. To really understand the massive kinetic energy we waste when we decelerate, just consider this quote. A simple bicycle coasting downhill loses 3 hairdryers worth of usable power strictly to the wind. In a standard gas car, all that kinetic energy is just turned into useless, wasted heat by your friction brake pads every single time you stop. Modern EVs solve this by recapturing that wasted energy using kinetic energy recovery systems, or KERS for short. By essentially running the electric motor in reverse, it turns into a generator. It captures the energy normally lost as heat and sends it right back to recharge your battery while you brake. This tech actually originated in Formula One racing, and it extends the life of your physical brake pads while making that amazing one-pedal driving possible. All right, our final section, Section 6, electrifying the last mile. It's not just passenger cars getting this tech. Get this. By 2031, the global electric commercial vehicle market is projected to reach an astounding $405 billion. This massive shift is being driven by the explosion of e-commerce parcel deliveries, needing last-mile electric vans, along with massive heavy-duty electric transport trucks replacing diesel across our highways. But as we electrify our world to solve the emissions problem, it leaves us with a final, pretty provocative question. Think about it for a second. Are we just quietly swapping out the dirty engines for clean batteries so we can sit in the exact same traffic jams? Or is this our once-in-a-century chance to completely rethink our entire car-dependent society and actually redesign our cities for people rather than just machines?